Thank you, Daniele, and thank you to all the organizers for inviting me. It's a great honor and pleasure to be the sole mathematician among physicists. And oh, I'm so yes, well, right. So yes, thank you again for having me. Now, Firenze is of course a beautiful place, and the weather has been well. But in any case, yesterday I walked through the city, and for a brief moment or for a while, I was in. Why is this not coming? Sorry. That appears to be so. But now, of course, I'm completely lost. Share screen. Why I am not. Ah, sorry. There might be another reason why this is not sharing. Oh, there we are. And I was in Santa Croce yesterday afternoon, and to my great delight, there is the monument, the grave of Galileo Galilei. And I thought I should share this, and I was even further. So while I was moved and humbled to have him, to see him there, 2 minutes later, while I was walking out into the cloisters, I walked past David Broadhurst, which humbled me even more. And I thought I was in a British novel, society novel, A Room with a View. Right. So let me start the talk again if I was ever going to find my slides again. And now, of course, we have the same thing again. Why are we not? Stop share. Oh, there we are. I apologize that this took a while. So there we are. So this is a math talk. I'll try to be as elementary as I can, and I hope that at various occasions you will see that the mathematics I do might be also interesting for you. And right, let me start very elementary with some really classical number theory, namely the number of ways how you can write a given integer n as the sum of m squares. And we denote this by Rmn. So there's a bit of a funny way of counting, so order matters, and a squared and minus a squared are two different squares. So the numbers are a bit higher than you think, and you would like to have explicit formulas, at least for small m. And indeed, Jacobi in 1828 gave this formula for the sum of four squares, which also then solved a problem, I believe from Legendre or Lagrange, 30 years earlier, who wondered whether every integer can be written as the sum of four squares, and yes, it does. And in case you wonder how this works, so say if p is equal to 3, we need to find 32 ways of writing 3 as a sum of four squares. Now this actually does work, namely, first you have to specify in the sum of four squares where's the 0. So it's 1 plus 1 plus 1 plus 0, but the 0 could be at 4 slots because of the ordering, so that's 4. And it's 1 squared and minus 1 squared, so that gives you two possibilities each. So this gives me 8 times 4 is 32. And it also works with others, and there are also some other very nice properties. For example, the number of writing something as writing 15 as the sum of 4 squares is the number for 3 and for 5 multiplied, and then you have to divide by 8. But this is called Hacker theory, which does this for you. So there's even more structure to it than here. And indeed, we have similar formulas for 2, 6, and 8. And I will say a word why this no longer works for 10 and higher. And I have also omitted the odd number of squares. Right. So how do you attack these things? And of course, you all know this is you look at the generating series of these representation numbers, which is a theta series, which for this purposes is the sum over lattice vectors of something which then hopefully converges. And when you sort them by the length, you get exactly the sums of squares. And more generally, we can do this for a lattice, positive definite lattice. And even in that context means you only take integral values and you have the same thing. And I would like to note why we might care about this also from a physical perspective is if you look at the function e to the 2 pi x dot x, which is a function on the torus, then this is an eigenfunction under the Laplacian with the eigenvalue of the length of the vector x. So these representation numbers are exactly the multiplicity of the eigenvalue n for the Laplacian on the torus. And of course, the key view is that we don't view q as a formal variable, but as an analytic variable of the upper half plane, e to the 2 pi tau. And in this talk, tau will be always u plus iv. I apologize for everybody who has different connection, different conventions. I suppose one reason is if you do have a Jacobi form variable z around there, you do want to call z x plus iy. So it's a holomorphic function on the upper half plane. And the theta transformation formula tells you that this theta series behaves very nicely under the transformation tau goes to minus 1 over tau. It basically, you get the theta series back up to a dual lattice, which all these aspects I will largely ignore during this talk. You can make this vector valued, this was already mentioned this morning, or you look at this as a modular form for a congruent subgroup of SL2Z. This is a bit technical and we won't go into this in this talk at all today. So, and Poisson summation, so a factor of harmonic analysis tells you basically that these theta series are modular formed. And I won't specify the level, it can be explicitly determined. You can also sum, not sum over the entire lattice, but over a shift of a lattice, a so-called coset of a lattice, but it all doesn't matter, at least for the purposes of this talk. And for the sums of squares, it's just the standard lattice with the standard inner product, and the level turns out to be 4. And, and how you can then find explicit or an asymptotic formula for these representation numbers is you identify the theta series explicitly as a modular form, which usually works very nicely because you're sitting in some finite dimensional vector space, and if you have enough information about this, about the structure of the modular forms in this ones, you can do this, and then you just compare the coefficients. And if this might be out of reach because the space of cusp forms is too complicated, at least you might get some asymptotic formulas. And for the sums of 4 squares, this is has weight 2 and level 4, and the space is two-dimensional, spanned by these Eisenstein series, where E2 is just the holomorphic Eisenstein series, which is non-modular. But if you look at these slight linear combinations of those, they do become modular. Or the easiest way of seeing this is you think about the non-holomorphic completion of the Eisenstein series, and this linear combination exactly kills the non-holomorphic part, and there you are. And then if you start comparing coefficients from there, you directly see that for the, at least for n odd, you get the formula just claimed. And you do the same thing for 6, for 2, 6, and 8. For higher n, the space then is no longer generated by Eisenstein series, so getting explicit formulas becomes more complicated, but you can still then find very nice asymptotic formulas, because the Fourier coefficients of cusp forms grow much slower than the ones of Eisenstein series. You forget the cusp form for the purposes of this in there. And I would even argue that sometimes this is better than having explicit formulas. We do have formulas, sometimes proven via combinatorics, but they become increasingly complex that you can no longer see actually what it is. Right, and as you know, you can play the same game. Say if you have the E8 root lattice, I've given here even the directions, then you have the advantage that this is a unimodular lattice, so the associated theta series is a modular form for SL2Z for the full modular group on the nose. And dimension is 8, so the weight is 4, the level is 1, the space is one-dimensional, spanned by the Eisenstein series. So we get the formulas for the lattice vectors of a given length in the E8 root lattice, 24 times sigma 3 of n, where sigma 3 is always the divisor sums. And of course, we always have the Eisenstein series, I mentioned it before, of arbitrary weight k and of level 1. But as I mentioned before, sometimes you no longer span the room, or very quickly you no longer do. But as Daniele just said, is you just forget about the cusp forms, because their growth is much slower than the growth of for the coefficients of the Eisenstein series. And you can also find linear relations between these representation numbers, because typically the number of equivalence classes of these lattices of a given dimension and discriminant grows quicker than the space of the modular forms. So you very quickly you run into the cases where you have linear relations, which is also fairly surprising. I always find. Right. But I would like to talk about indefinite quadratic forms. Now, if you go back, where have I defined them somewhere? We do have a problem. Namely, if your lattice, your quadratic space, underlying space is no longer positive definite, the series here, which is defined here in the middle of the slide, can I do this without, which one is the top one? This series would no longer converge, because you have vectors of negative length. Or in the same way, and I'm not quite sure how to make sense of this. Of course, I'm a mathematician, I'm not a physicist. Or alternatively, these representation numbers would be also infinite. You would have simply infinite number of vectors of a given length. unless in a very particular case. So this no longer works, so we have to work a bit harder here to find theta series associated to indefinite quadratic forms. So these are some examples of indefinite quadratic forms. The middle one is, of course, exactly, well, minus the discriminant of a binary quadratic form, and so on. And so, as I said, we are now in trouble. But there are plenty of examples of indefinite theta series which give rise to modular forms. Namely, the first one is, it's not necessarily due to Zagier, but he has championed this. So there is our Eisenstein series. Well, and you write the divisor sum in the following way. Well, you write n as your divisors as the product a times b, and then the divisor d to the k minus 1 is then a to the k minus 1. And you sum over all the positive a and b. So that's an indefinite theta series because the quadratic form is a times b, signature 1, 1. Right, I put a polynomial in front of it, which is actually a harmonic polynomial with respect to the Laplacian, this indefinite Laplacian. So far this is not unusual, but then I just restrict to the positive cone and I get a modular form. Right, this is already fairly mysterious, and also how you get the Bernoulli number bk in front of it. Now, you can actually show the modularity of this by Poisson summation. I do not recommend this. It's a fairly nasty calculation, but moreover, for k equals to 2, that would give me the Eisenstein series of rate 2, something goes wrong, because then it's no longer modular as stated. So that Poisson summation actually works. You still always get an eigenfunction under the Fourier transform once you've defined this appropriately. The problem is Poisson summation for k equals to 2 collapses. And once in a similar situation, I wasted a year trying to make sense of this until I realized that Poisson summation wasn't holding in that case. And then it took me another year to convince my collaborator. Right. And no, what it is? I mean, what is Poisson summation? I mean, you have a series. You have any function which you make periodic by summation over your lattice, and then you expand this as a Fourier series, and then you have to worry about whether the Fourier series converges pointwise to your function, to your periodic function. And this sometimes, if your function is not sufficiently continuous or differentiable, this goes wrong. So it's Riemann-Lebesgue theory, these kind of theorems. When does or Dirichlet, when does a Fourier series converge to the function pointwise? So that's really what. Yes, then you have a better chance, but of course, then you would need to reformulate everything in terms of distribution or distribution valued modular forms. But then you're somewhere in a different ballgame. Yeah. Another one is by Hecke. So my quadratic form is x squared minus dy squared. Again, a signature 1, 1. And you let OK to be the ring of integers. So for the purposes of this talk, if D is congruent to 3 mod 4, it's just x and y are integers. And you have the units in there, so you have plenty of lattice vectors of length 1. And then you look at this one. namely you sum again over the positive cone, but you take only the vectors modulo the group of units, and you take the sign of lambda, where lambda you view as a real number, as x plus the square root of dy. Now, I say roughly here because, as stated, this vanishes for trivial reason, because lambda and minus lambda would give you opposite things. So you have to take a coset, but let me ignore this. But roughly speaking, you do get a modular form of weight 1 in this way. So again, you have a positive cone condition, but in addition, you have this group of units playing a role. Right. So let's think about a bit of the geometry of this. So you have your indefinite quadratic form. You can diagonalize this over the real numbers, and you just flip the signs to make it positive definite. So this is as explicit as something can do, and there is now your positive definite form, for which you can form a theta series. However, I have many other different ways of turning this into something positive definite. Namely, if I have 1, I just apply an element in the indefinite orthogonal group and play the same procedure, and I still have something positive definite. And my given positive definite one is fixed by SOP times SOQ, or OPQ, OPQ. And so the minimal majorance, the minimal means the smallest, turning something into positive definite one in the minimal way, is in a one-to-one correspondence of your Lie group G SOPQ modulo maximal compact. Or alternatively, it's in one-to-one correspondence to the negative definite subspaces of RPQ. If you have one, you take the orthogonal complement, and then you just flip the signs on Z, and there's your positive definite quadratic form. And the oriented one will play a role much later on, but you can ignore this. This is sort of fine details. It's not so important at this point. So there is our symmetric space associated to the orthogonal group. If you want to G mod K, G my Lie group, K the maximal compact, here explicitly realized in terms of linear algebra. And we write D for this, the space of the minimal majorance or the negative definite subspaces, the symmetric space to it. And we have plenty of examples for signature 2, 1 or 1, 2. D, my symmetric space is just the upper half plane, or if I take the oriented one, 2 copies of it, one the upper and the lower half plane. For P, 1, I have hyperbolic P space. And for P, 2, D is always Hermitian, meaning we have a complex structure on it. So for 2, 2, it's actually the copy of 2 upper half planes. And for 3, 2, there's another accidental isomorphism. You get the Siegel upper half space of degree 2. And for 19, 2, if you take an appropriate quotient of this, is you're looking at the moduli of polarized K3 surfaces. So, and of course, various variations of this, which of course play a huge role in what you are doing. I prefer to look at the signatures where, when there's a 2 involved as n, 2. I know very often you usually do the other signatures, so but for me this is more convenient if you guys let me get away with this. So what you then do is, in order to form a theta series, which goes back to Siegel, so you have signature P, Q, and you look at the majorant, one majorant or a negative definite subspace Z, you form the following series. You still sum over the lattice. You still do e to the 2 pi I x dot x u, where u is now the real part of tau. And in order to make this convergence in the V factor, you switch from Q to R. And again, Poisson summation will tell you that this gives you modular form now of weight P minus Q over 2. And again, you get some level. The level calculation is exactly the same thing you would do for a positive definite case. The price, of course, is you're no longer holomorphic. So these ones are not of the form we had before, when I said was referring to Zagier or Heck. And there is a huge theory behind this, which we call, the mathematicians, we refer to this very often as the Weyl representation, sometimes also called the oscillator representation, because of course it shows up in quantum mechanics. We refer to the underlying group, the Heisenberg group, which I understand you physicists call the Weyl group, which I find fairly amusing. So, and the stabilizer of L acts on this on the left, and the theta series is invariant under this. And we look at the locally symmetric space, which is the generalization of our modular curve of the fundamental domain in the upper half plane, of course. Of course, these are then, say, is the mod for 2,19, this is the moduli space of the K3 polarized K3 surfaces. Right. So, and the Siegel theta function is invariant under this. So it's a modular form in tau, and it's an invariant function on the symmetric space variable Z. Right. And what you can do is, with this, just as a preview of what's to come, is you use these theta series as an integral kernel of trying to move objects transfer objects from the orthogonal group to SL2 or the other way around. And that will be the basic theme for today. The question is what kind of kernel function you use and what kind of input you're putting in there. Yeah, yes. Yeah, it cannot act on tau because gamma is in the stabilizer of the lattice. It only knows something about the orthogonal group. Okay, so gamma is not the SL2 transformation. Exactly, yes. So generally speaking, yes, for the purpose of this talk, gamma is always the orthogonal group, the lines for the orthogonal group of the lattice. And if I ever use this, gamma prime, that would be SL2Z or a congruent subgroup. And the variable for the orthogonal group is always D. It's Z and D, and for SL2, it's tau. Here, well, it's P times Q in general. Okay, yep. Yeah, so that's the reason. So for me, tau is always upper half plane, Z is always in the orthogonal variable. And if you go through this calculation, ultimately, so you have the gamma up there, then you can move it into the sum of into the sum. It's basically an averaging process. You will see that it's quite immediate. Right. Before we actually write down the theta series, let's do a bit more geometry, because this will come in there. So we have X. D mod gamma. would like to know its geometry. Homology, cohomology, or whatever variance you have. So, and for this you would like to study nice submanifolds and potentially their generating series. And this has application number theory, representation theory, geometry, but also arithmetic geometry. And as I would like to argue, also in physics. So what are these submanifolds? I will refer to them as special cycles. So I start with a lattice vector of positive length. And then I look at the subsymmetric space of all the negative definite, of all the z's in D. These were the negative definite subspaces in my vector space, to which x is perpendicular to. So x is a positive vector, so you basically cut out one positive dimension, so you get a subsymmetric space of signature p minus 1 comma q. And you will get I will give now plenty of examples of this in a second. On this gamma x, the stabilizer of x, up here in the orthogonal group acts. You can look at the quotient, and you can then look at the image in x. And now I look at all of these guys of length n. Now there are infinitely many of those, but modulo gamma, it's a result by reduction theory. Think about, for those of you who a bit of number theory, the finiteness of class numbers. These are finitely many, and then you look at the collection of this. And maybe for a moment just as a formal sum. So 1, 2. And now, Ollie, you need to be careful. Now I have two upper half planes. The symmetric space, this is an upper half plane, and that's also an upper half plane. Forget about that one. This one. Signature 1, 2, I cut out one negative thing. So I get signature 0, 2, that's 0 dimensional, you get a point. And what you get is you get a CM point, a point which is, you implicitly mentioned them in your talk, David. So these are the quadratic irrationalities in the upper half plane. So these are the roots. I will write them down explicitly in a later slide. So you have your quadratic equations over the integers with ABC. So ax, what is it? Ax squared plus bx plus c equals to 0. Negative discriminant, you get two roots, one in the upper, one in the lower half plane. You take the one in the upper half plane, and a, b, c are integers. Discriminant minus n, and that's a CM point. We love them. And I hope by the end of the talk you will love them too. So you can write them down fairly explicitly. Yes, exactly. And that's the class number, modulo S of 2z. So for 2, 1 now, it's different. Now comes the difference between 1, 2 and 2, 1. You cut out a 2, which becomes a 1. Symmetric space of 1, 1, that's just a real line. Now you get a geodesic in the upper half plane. So 2, 1. Upper half plane is my symmetric space. Only that one, not this one. So I get this one or that one. So, and depending on this is, so they might lie in the, and then you look at this in the image in the fundamental domain, say, where it might become an infinite geodesic, might stay an infinite geodesic, but typically it becomes a closed geodesic, a closed curve. inside there. And then you look at all of those coming from n. Now this has something to do with, given n, with a class number of real quadratic fields, never mind. For p, 1, you get general hyperbolic manifolds of dimension p minus 1 embedded in the 1, which is 1 larger. And for p, 2, remember there we have a complex structure. P minus 1, it has real codimension 2, complex codimension 1, and that's known as a divisor. So you produce an entire zoo of interesting cycles in this way. Right. And now you look at this generating series of these objects, which I wonder, and I will ask you this again at the talk, well, I call this generating series, is this some kind of partition function in the sense, in your sense? Because we're counting certain things here. In particular, for signature 1, 2, 1, no, 1, 2, we're counting points. So you can count the number of them and look at the generating series of them. And that's what we will do in a second. Yes, roughly, yes, it's a class number if n is a fundamental discriminant, yes. But yes, think about them as a class number. It's called the Kronecker-Horwitz class number, it's a class number. So now the theta series. So whenever you have an eigenfunction under the Fourier transform, you can form the theta series, you get something modular by Poisson summation. If Poisson summation works, but say. And the ones I consider are the ones which were explicitly constructed by Kuttler and Milson some time ago, in much greater generality. And you should think about this as one which is of the type of Siegel, which are written explicitly constructed before. So it has the majorant in there, it has some non-holomorphic terms, and so on. But I won't write them down explicitly. The Hermite polynomials show up, so it's fairly explicit. You can write them down, but there's no need to know them explicitly. But as a function of tau, it's modular of weight p plus q over 2. And note that this is the weight as if this was a positive definite space. It isn't. But it's non-holomorphic. So like in Siegel this was a p minus q over 2. And as a function on the orthogonal symmetric space, it's actually a closed differential form of dimension q. So, which descends to a form on your manifold. So with Siegel, we had p minus q over 2, and you had a function on D. Now we have a differential q form. And the idea is you can use this one now as an integral kernel. So namely, you take a compact q-dimensional submanifold of X, and you integrate the theta series over that submanifold compact. And the beauty is, you're doing something in the orthogonal group. Tau, the SL2 variable, is unaffected. The left-hand side is a modular form, because the theta kernel is modular. It might or might not be holomorphic, but it's modular. A priori, you haven't done anything, you don't have to worry about anything. You have written down something modular. And the theorem of Kuttler-Milson is, if you do this for, by the way, compact you recall, I'm a mathematician. I'm a bit whimsy about convergence. Then this gives you a map on the level of homology to the holomorphic modular forms. Even though the theta kernel was non-holomorphic in term, after you integrate the orthogonal variable away, you get something holomorphic. And with my submanifolds of that codimension Q as before, the Fourier coefficients of the holomorphic modular form are the intersection numbers of the subcycles with that curve C, say with the other homology class C. And note that again, if I write this down and so on with Zn, this is a summation over the positive cone. I've thrown away all the negative vectors, convergence becomes fine. Well, it's not so clear that it's fine. But it's clear because the theta series converges nicely and I integrate over something compact, I don't have to worry about convergence. This works. Whereas if I start here, I might have to worry about it. So this gives you a universal way of constructing holomorphic modular forms out of an indefinite theta series. And now you can worry about all things. Is this map surjective, injective, and what other properties this has, but we won't go into this now. Or you can do the same thing, but not integrating over cycles, but integrating against a differential form of the complementary degree, maybe with compact support. And then, again, you get a modular form. In the same way as before, and then the Fourier coefficients are the periods of eta over these cycles. It's the dual statement, it's the duality between cohomology and homology, which does this. In fact, that's the one which you can prove by some explicit calculations. So, right. So we have plenty of ones, but I would like to now vary on these two themes where the hypotheses, implicit hypotheses, are not fulfilled. But maybe let's do one here. 2,1, the geodesics in the upper half plane. Right, so we have signature 2,1. Say it's b squared minus 4ac. The associated symmetric space is the hyperbolic plane. Not that one, this one. And D might be a modular curve. It's non-compact. And if you write down explicitly what the geodesic is, here's your equation, A modulo z squared plus B real part of z plus c is equal to 0. So you can actually nail this down. There is and this defines your geodesic as long as the length b squared minus 4ac is positive. So we can write this down fairly explicitly. You look at the quotient, you look at the sum of all these guys. And when you then have a closed curve, then the generating series of the intersection of the closed curves with these geodesics gives you a holomorphic modular form. Right. And here in the last one I've written down explicitly, that this is really a summation of a positive cone. For technical reasons, here H is a coset of the lattice. This is, just ignore it. Otherwise, the whole thing would be identically 0. You have to orient the cycles, the geodesics. No, we're not doing this here today. Right. And in fact, it's a cusp form of weight 3/2, but it's not so crucial. 3/2. Well, it's always, the weight is always P plus Q over 2. Right, But now let's do the same thing for signature 1, 2. Well, let's say it's 4ac minus b squared. Again, I have the upper half plane. And here is my cycle, my CM point associated to this. A, B, C are integers. So it's the root of az squared plus bz plus c equals to 0. And there it is. There it is, modulo SL2z. So you can move them into the fundamental domain. You only get finitely many of a given discriminant, and that's exactly the class number. And these are the CM points which showed up in David's implicitly. And now this is why this slightly differs, is you do have to worry about the stabilizer of gamma in there, but let's ignore this. This modulo is going to come. That's exactly the next term. So I have these guys. And I can take their degree. I count them, slightly weighted. And if you want to, this is really the analog of the representation numbers in a positive definite case. I was counting the vectors here of given length n. This is now infinite, but modulo the orthogonal group of the ladders, this becomes finite. And now I can write down the generating series. And these are the so-called Kronecker-Horwitz class numbers. And there's a theorem of Zaghi from 75, which I reproved in my thesis, is that the generating series of these degrees, well, okay, there's a constant term which we ignore, is a modular form, except it isn't. And the reason is implicitly we're integrating over something non-compact or against the non-compact function with non-compact support 1. Hence, the prerequisite of Kuttner-Mills not quite fulfilled. And indeed, you get some non-holomorphic terms behind there is. And as a preview, this is a mock modular form. And this one, this gives rise to the shadow. It's going to come. It's going to be, well, the shadow has weight 2 minus 3/2, so it's 1/2. It's Jacobi theta. Right. Yeah, well, it's against the invariant measure, and then appropriately normalized by 1 over 2 pi or minus 1 over 2 pi. Well, here you can see it here, so that the volume is minus 1/12. Okay, so here normalized with 1 over 4 pi, minus 1 over 4 pi. And the non-holomorphic terms you see is an incomplete gamma function. And I call this Eisenstein series is of weight 3/2. So sorry, Daniele, down there, this script is the weight, and the S variable is there, and the way how I normalize it, it's 1/2. So it's non-holomorphic, but basically it's a weak mass form in my sense. Here's the mock modular form, and that's the shadow, which will be the completion. And just for fun, there's a famous formula of Gauss that the sum of 3 squares can be expressed in terms of these class numbers. And this pops out of this is what you play is you run this with 2 different lattices. So one of the advantages of the Theta machinery is you don't care about the lattice. Well, you can just carry it on. You're not restricted to SL2Z and so on. And you construct them so that they lie in the same space but have the same non-holomorphic part. Take the difference, the non-holomorphic part cancels, you end up in a space of holomorphic modular form, which is one-dimensional, which is spanned by theta cube. And then you get this result. So if you're interested in these kind of things. So, right. Oh, beautiful. Well, 10 minutes. Harmonic means forms from the mention them is so. I suppose Bonnier and myself, we were the first one to identify this as a space, even though these objects already occurred at least since the 70s. And then we gave them the name harmonic weak mass forms. Namely, these functions are modular of weight k, level n. Of course, implicitly, they already also showed up today, this morning. You do allow linear exponential growth. You're an eigenfunction under the weight k Laplace operator. And if you apply a certain differential operator, you do get something holomorphic of the dual weight 2 minus k. And these objects can be written as holomorphic plus a non-holomorphic part. The holomorphic part is the Mach modular form, and the shadow arises from the non-holomorphic part by applying this differential operator, which kills the Mach part, but turns this into a holomorphic modular form of weight 2 minus k. So for Zaghi, you get the Jacobi theta series of weight 1/2. And while Bonnier and I, we were thinking about this in a completely different context, at the same time, Swegers in his thesis constructed harmonic weak mass forms by looking at Ramanujan's Mach theta functions and completed them to become modular, which then afterwards one could interpret this as in he cooked up a harmonic weak mass form associated to this, depending on your taste. And Zaghi's Eisenstein series is such a harmonic weak mass form. And this has quite a few applications in arithmetic geometry and combinatorial number theory, but also in mathematical physics. Not only here, but also say in the moonshine business. Moonshine business. Right. So, and the next slides are because of a discussion I had on was it on Monday? No, Tuesday with Ollie. So these slides are all Ollie's fault. So we are again in the CM point case. Upper half plane, signature 1,2, my cycles are the CM points. So what you can do is, you have some modular objects, invariant objects under SL2Z. Here the explanation marks means it's weakly holomorphic, so you do allow for poles in the cusp, so say like the J invariant. And what I do is I take my function f and I sum it over all the CM points of a given discriminant. If I take f to be the constant function, then I get the class number. But I could take f to be the J invariant, say. And indeed, that's what Zaghi had done in 94, but he only publishes in 2000, that if you take the J invariant, get rid of the constant term 744, and you write the generating series of these traces, as he called them, you get a modular form, again of weight 3/2, 4 gamma 0 form, and it's weakly holomorphic because you do have a bit of a pore. And the values of this are, at these Hegner points is another name for CM points, they are known as singular moduli and of really classical arithmetic interest. The values are algebraic and generate something which is called a Hilbert class field. Never mind. So we really care about these values. I forgot now, Daniele, to mention what happens if n is equal to minus 100 or 163. Never mind. Right. If you look at this series, you might have several questions. First of all, how did Zaghi prove this? Zaghi really showed that that the modular curve has genus 0. It's a genus 0 Riemann surface, and it generalizes to other Riemann surface of genus 0, where you then, David, you use the Hauptmodule for this instead, which means y genus 0. What's the meaning of this negative coefficient? What's the meaning of the constant coefficient 2? And why on earth is this holomorphic? When we took the trace of the constant function 1, the class number, we were getting something non-holomorphic. And what Bonnier and myself, we looked at this and said, okay, I have the Cutler-Milson kernel for signature 1, 2. I can integrate this against f, my modular function, my J invariant, if you want to, over the fundamental domain. Right, and I do get something modular of weight 3/2 because the theta kernel has this property. Except, of course, I have to worry about convergence. But the miracle is, and it's a non-trivial fact, while f blows up, the theta kernel wins. It decays even quicker. This is a particular fact in this case and so on. This happens not in general. Generally, these theta kernels are moderately increasing. So that actually converges, but it does not converge term-wise. It's a very delicate thing that this is there, so you have to be careful. But you can at least write this integral down. How you calculated this then is a different question. And then you have to regularize this. And you define a trace of f to be, well, the trace as before. The trace at 0, you define the average value of f over the fundamental domain. Now, that definitely does not converge. You have to regularize this one. And basically, in the most elementary way, you cut off at a certain height and let t go to infinity. And for negative... I suppose. But of course, you... Yeah, yes, I would think so. Yes, yeah, yes, yeah. Oh, this is a truncation variable, yeah. I haven't thought about this in this way, but yes. More thought about this in terms of Borchert's, what Borchert stuffs. Right. And indeed, if you take any congruent subgroup for SL2Z, you look at the modular function for this, and you assume that the constant term of f vanishes, all of them. Then the generating series of the traces, here slightly modified for the constant term, what happens at the negative ones, gives you a modular form of weight 3/2. It has nothing to do with genus 0, it's just true. The constant term is some regularized value of f over the fundamental domain. The Fourier coefficients of negative index determine the polar part at infinity. And for this to be properly holomorphic, you need that the constant term of f is gone. If the constant term is then you do get some Zaghi type non-holomorphic terms again. Well, because your weakly holomorphic modular form has a pole of certain order at infinity. And therefore, the sum here goes over the negative indices. So that's the bound. So it depends on, so if your pole is of order 10, then it cannot get worse than that. Yes, yeah. Oh yeah, this one is finite. Oh yeah, definitely. That's a finite sum. Absolutely. This is, no, it's not even so clumsy. It's actually fairly explicit. You can write this. Because these are the negative term, minus n squared. In that case, negative index corresponds to geodesics, because we're signature 1, 2. And for the geodesics, if the discriminant is a square, then even in the quotient they are infinite geodesic, going from cusp to cusp. And that's why the reasons they show up. So it's somewhere, it's in the geometry, it's again hidden in the geometry. Well, here's an example for you guys. So gamma 0p, so these are, C is divisible by P, and I extend this by this group, so gamma 0 star, so you look at the Funke extension, and of course, these are some cases which also show up in modular moonshine, because when they have genus 0. But they don't have to be genus 0. You look at a modular form for this group, and here is your explicit function. Here is the explicit formula. These are the traces of the CM point. This is the constant coefficient, the volume, which we can explicitly calculate in terms of Fourier coefficients, and also these ones, the negative ones. So only this is as explicit as you can have it. Right. Now, sorry, I cannot resist. How much time do I have? No, folks, let me skip the next one. Saying is, you can play other interesting games here. You can plug an Eisenstein series into the lift, and you get something interesting with general parameter S. You can take derivatives, you can play all kinds of things, and you always get something interesting. The reason why I put these things in there is you can write down log delta, where delta is the discriminant function, and you get something interesting. You get the derivative of Zagi's Eisenstein series, and this plays a role in arithmetic geometry. Yeah, yes, of course, relatively to respect to S, yes. So you can play all kinds of games there and you get something interesting. And then only rediscussing there is, then I started to wonder, what about the modular graph functions? There's nothing which prevents you of plugging them into that theta kernel, that theta machinery. You will get some traces of these over the CM points and some non-holomorphic part, which I don't know what it is. So the question to you guys is, would you be interested in this? Right, so the next slide is courtesy of Daniele, who wanted to hear something about the Borchardt lift, the Borchardt's theta correspondence. So we have signature p, 2. You can think about p equals to 1, which we had before, but for general p is more interesting maybe in this one. And we had the Siegel theta series, which was weight k, p minus 2 over 2 in tau, and it's invariant under z. And what Borchardt does is, well, you take your weakly holomorphic modular form. So here, two slides in the typo, two typos in the slides. This should be subscript sub n, and here should be an exclamation mark so that it's weakly holomorphic. And the weight, I'm sorry, and the weight should be minus k. Everything is wrong in these slides. I have to admit, I wrote these slides after lunch. So it's minus k. And let's assume they have integral coefficients. Then you can look at the integral of the theta function against f. F has weight minus k, theta has weight k, the product has weight 0. You can integrate it over against the invariant measure over the fundamental domain. But now this has to be regularized. The theta function is moderately increasing in tau. F blows up exponentially. It can be regularized. And in fact, you guys did it. Harvey and Moore. And then Borchardt split this up and turned this into a much more general theory. And once you've done this, you will see you get a nice function on the orthogonal group. It has logarithmic singularities along the special divisors which are introduced before. So for signature 1, 2, it would be along the CM points. And the singularity, and the one which show up is the polar part at infinity of f. And what phi is, it's roughly the logarithm of an holomorphic form for the orthogonal group, and which turns out to be having an infinite product expansion. And then Borchert's derived all kinds of denominator formulas for all kinds of Cauchy-Lie algebras and so on. So a zillion of applications there. The example, maybe simplest example, signature 1, 2. You need to have weight 3/2, weight 1/2 as the input, and you can take the Jacobi theta series. Okay, 24 times. And the output of the Borchert's machinery is the discriminant function. And note that since here theta has no polar part, you don't have a divisor, and this corresponds to that this converges on all the upper half plane, and yes, and is never zero on the upper half plane, only at infinity. So, right. Now you wonder what has this to do with the stuff I'm doing, except that it involves theta series. Well, what Bonnier did, he extended the Borchert's lift to harmonic weak mass forms with for all kinds of reasons. But even though you no longer have a product expansion, but then what Bonnier and I showed is that there's a duality between the Borchert's lift and the Kuttler-Milson theory. You take the weak mass form, and it has a shadow in the sense of Zagier. And then there's a duality between the Borchert's and the Kuttler-Milson lift, namely phi, the function on the upper half plane, no, on the orthogonal group with logarithmic singularity. You can take the differential operator, the exterior derivatives, del bar, which turns this into a two form, a differential two form. On the other hand, on the orthogonal group, on the other hand, you can take the Kuttler-Milson lift. You take the Peterson inner product for SL2 against the shadow. In the z variable, that's still it was a two form and it remains a two form. And these two things are the same up to the Kähler class. So that's how this relates. So Daniele, so if I go over time, I blame it here on two of you guys. So, right. But now actually to the thing which I wanted to talk about. Hyperbolic p-space. Let's think about 2, 1. Good enough. So good enough. 5 minutes. So in p-space, I take two vectors of negative length, C1 and C2, and I take the inner product to be less than 0. And I take the error function, the good old error function from statistics, that one. And then what Zander showed is, if I sum over the lattice, again, I need to coset, ignore this, evaluate x against C1, x C2, plug this then into the error function, v is the imaginary part of tau, and write down the generating series of this, but however, for all vectors, also the negative vectors, that this becomes a non-holomorphic modular form, and in fact, roughly a weak mass form or mixed modular. But moreover, what you can do is you can separate this into the error function into sines and incomplete gammas. This bit is only for positive vector x. This is your mock modular form, holomorphic, and this is the non-holomorphic completion. And this becomes a modular form, or a weak, or Yes, it is. It is in it. Yeah. Yes. Let me. Yes, ask me some other time. Okay. Okay. Note for this one, convergence is not clear at all. You have to really worry about convergence. And the way how Swegers shows us is he uses Poisson summation, which really is implicitly, however, he shows that there are certain differential equations which are fulfilled, and then he has to worry about that he can actually is allowed to use Poisson summations, certain convergence, which is actually a pain. It's rather delicate. I mean, and the other thing is just seeing that this is the completion is marvelous. Right. And Kuttler and myself, at various points, independently, we looked at this and realized that we can explain this or obtain this via Kuttler-Milson theory. The vectors C1 and C2 in hyperbolic space define you a point. I mean, after all, they define you a point in the hyperbola, a point in hyperbolic space. Here. Here's C1 and here's C2. They're vectors of negative length, hence they define your point in symmetric space, define your point in the upper half plane. Signature 2, 1. And the condition that the inner product is negative means that they're both in the same connected component. I mentioned, I mean, after all, it's a hyperbola of two sheets. You better want to get them in the same component. This was what these conditions mean from Swegers. I take any curve which connect these 2 points. The Kuttler-Milson form is a one form. I can integrate over this curve. This converges because I'm integrating over something compact. Even term-wise, I don't have to worry about anything. And what I get is Swegers thing. And I don't have to worry about what curve I take because the Kuttler-Milson series is closed. And the Mach coefficients, these difference of the signs, this is the intersection number of these cycles dx with this curve, or if you want to linking numbers. If the 2 points are gamma equivalent, then they close up in the fundamental domain. You're integrating of something close and you get something holomorphic. The non-holomorphic tail in Swegers vanishes. If C1 and C2 are gamma invariant because you basically can move these things over and you get 0. And you can also allow C1 and C2 to go out to the cusps rationally. Then you do have to worry about convergence or everything. It also works in that case. And you can also play similar games in higher weight, and Zagi's interpretation of EK is hidden there as well. And then Alexandrov, Banjari, Manchot, and Piolin in 2016 generalized Swegers results in the following way. So they have 4 vectors of negative length, C1, C2, C1 prime, and so on, with various conditions. They introduce a higher error function, E2, a higher one, and Z is the span of C1 and C2, say in this one. And then they write down the big brother of Swegers thing. Now I have 4 E2s corresponding to all pairs of C of these Cs. And this becomes non-holomorphic Mach modulo or mixed Mach modulo of depth 2. So it has a holomorphic part, the Mach part, plus a non-holomorphic one, similar to what we'd had before. And I won't have time now to read out from the introduction of the paper. This does show up in string theory type 2b, and with instantons left and right, and I leave it for you to think about that. And Kuttler and myself, in various papers, we reinterpret this. And so my symmetric space is the upper half plane. Two vectors of negative length. They span, and if they're right, they span your -2 plane. -2 planes are points in the symmetric space. One. And if their conditions are right, they define you all points in the same connected component. Z1, Z2, Z3, Z4, and so on. Z5. Coming from C1 and so on. In the ABMP case, there were 4 vectors, but now we can write down 5. Various things is, I take geodesics connecting these curves. I'm doing the same thing. I take a surface which bounds this curve. I have a 2-cell, which I can integrate the Kuttler-Milson form over. And what you get is exactly, well, for 4 points, the appropriate thing is ABMP, but it works in general. For any n-gon constructed in this way, ABMP had made a conjecture, what comes out there in general, it turned out to be not quite correct. And in fact, this constant omega can be explicitly calculated. If you write down the wrong thing, the whole thing doesn't converge. Whereas the left-hand side converges term-wise because you're integrating over something compact. Always. And it's the modular completion of the generating series where you count the number of CM points in your surface S. And we can do this for general signature P, Q. You can do this for Lie dodecahedron for signature P, 3. You get some beautiful formulas. There were also other people like Martin Raum, but also Nazaroglu, who worry about these things and other signatures in other situations. Right. And here are some explicit values what you can get for these constants. You can explicitly calculate these numbers omega c here. So for n equals to 4, there it's 0. That was the ABMP case. If you have a triangle, it's always 1. If it's a pentagon, well, it's -1 or 3. It's -1 if you connect them like this. But if you connect the points like this, in this form, you get 3. Right. And we have some work in progress, but the real point is we have these symmetric spaces which play a role in physics. We have these sub-manifolds, these special cycles, which come in the most natural way. They must have some meaning in physics as a partition function on something. You take these cycles, you do something with them to get numbers. These got to have a meaning. Thank you very much. Mm-hmm. I haven't thought exactly what, well, hang on. So these are, they do have some modular interpretation, yes. Oh, you mean, so it's in subs of 18,2. I forgot now what it is, but there these manifolds do, the submanifolds do have a modular interpretation, but I forgot now what it is. Was that the question?
Well, yeah, my question was, is there interpretation of this key submanifold in terms of geometry?
Yes, there is. Yes, they do have a modular interpretation. Yes, in terms of the K3 surfaces. But ask me, and since we share the office, we should be able to talk to each other. This one. P odd? No, it's rather Q, the second variable, which makes a big difference. And for us, it makes a difference because I haven't said anything. These cycles need to be oriented, and when Q is odd, the cycle coming from x and minus x have opposite orientations, and they cancel each other out. Whereas when Q here is equal to 2 is even, then they have the same thing. Of course, in complex geometry, you don't have to worry about orientations. They are just what this is. So that's one aspect. Yeah, so that, but this maybe wasn't answering your question. Okay, good. Q is sort of the mix. It's interesting enough that the P, once you can do it for one P, you can do it for all. And also the lattice doesn't matter. These things, this work for all lattices. Maybe at the expense of how explicit you could write it down, but that's David. You had a?
Yes, I have a very specific question.
Okay.
I asked it in a similar context to Francis Brown,
Mm.
couldn't give me a straight answer. So, in this particular case, Francis quasi-interiors with non-homomorphic partners of cluster forms
Mm-hmm.
get intersection numbers between them. And that involved integrating up to, let it goes infinity,
Mm-hmm.
things which have inverse bars of 1 upon q and log q.
Yep.
And I said, how do you regulate that?
Regular.
He couldn't give me a straight answer.
Oh.
So I did it myself.
Mm-hmm.
I did it the only way I would know.
Yeah.
I have inverse bars with variable logarithms. I took Adam's finite.
Mm-hmm.
And although Francis didn't know that that's the correct answer, it's the one that works. So now I ask you, if you have some comparable situation at which the trust you have inverse bars of q and logarithms of q, and do you take Adam's finite?
What did I do is, okay, I might or might not. We had this actually in a similar game, not quite this one, is where we were trying to calculate, it turned out to be, the J invariant does not have an L function. But let's just assume it has one. And then you would like to take it as a central point 0, which certainly makes no sense. Really, what it means is you integrate J from 0 to I infinity. And we had a way of making sense of this, or exactly Don had in one of them. This is, and maybe I share you this way how he does it, and then we can talk about whether it's the same or not.
You see, if you just have Adam's, it's like the way you think of the terms in the law. With what Adam's said, if you're calculating integrals of the singular and also another z,
Yeah, yeah.
If you can make it finite by taking finite polynomials in log and 1 over x, and that's the thing that gave the answer.
I think we do something different there. Okay.
Now Francis said, oh, I never had to do that because I informed my contour in some way.
Yeah. Okay.
I think I saw the
Oh.
integral there. When you had the integral with red at the top, what was the form of the singularity? But when you turn to the audience.
Oh, you mean the well, it was over the upper half plane. I mean, over the fundamental domain. So there was simpler. Well, you cut off the fundamental domain at a certain height, calculate it there, do the x integral first, and then you let t go to infinity. But let's talk about this. All right, okay. So maybe there is hope.